Testing. All right, good morning, everyone. Thanks for coming down. They managed to push me out one room more than last time, so anyhow. So yesterday I did a session on spaces. This session is also on spaces, so there's going to be some repeated material, but I guarantee you'll get some value out of the session. We do some more deep dives into some of the case studies, so you can understand, what customers were using before, what their problems were, and how spaces gave them the benefits that they saw. So I do guarantee some additional value out of this, and of course gives you extra question and answer time. So in this talk, we're going to understand the what, why, and how of spaces. What is spaces? What are the components that comprise it? Why should you deploy spaces? What are the benefits you're going to get from it? And how? How do I all put this together? And I'm going to throw in the PowerShell demo that you saw in the last one, if you saw the last one, because a lot of people got good value out of that. I'm going to grab the clicker here. We're also going to present the solutions that are available and certified today. And we're going to show you how customers today are using these solutions to solve real-world problems and get a number of benefits. First, a little background to why we've designed spaces and what we've designed spaces for. In recent years, there have been an absolute explosion of the amount of data that's being generated and the amount of data that's being available. Devices are everywhere. We have lots of apps and services. We have all new types of service models. We have cloud computing. We're having a big shift into how data is consumed and how we're handling that data. This is not unique to This is not unique to the industry. I mean, Microsoft, we design large service platforms. Some examples are Bing and Azure. And we also have lots of large private cloud infrastructure as well. And looking at these infrastructures, we found that they shared a series of similar design goals. Number one, you need to use cost-effective hardware wherever possible to meet your budget requirements. As you scale, you have to scale in units that are affordable. You need to minimize failures wherever possible, reduce single point of failures in your deployment, because as your deployment scales, those single points of failure will potentially bring down the entire thing. You need to build in handling of resiliency in your cloud. And again, as your deployment scales, as your cloud scales, you need to minimize any inefficiencies in operations, because those inefficiencies will not scale to meet your increasing data needs. So these are some of the three lessons we learned from looking at some of the existing ways that we've deployed storage, how we handle it internally. And taking these three, we've sort of looked at them, and we've designed spaces around them. Now, in this release, one of our focuses have been to dramatically lower the cost and complexity of deploying and managing storage for our most cost-conscious customers, which include those that deploy infrastructure as a service storage platforms, such as hosters. Now, we've achieved this in two ways. Our approach has been two ways. Number one, to disaggregate compute and storage, to ensure I can scale these independent of one another. As my compute needs grow, I scale my compute independent of my storage. As my storage needs grow, I scale my storage independent of compute. These two are not inextricably tied anymore. Second way we're achieving this is by utilizing industry-standard commodity hardware where possible. This dramatically reduces the cost of deploying my storage. We use commodity JBODs with commodity disks in them. We use commodity servers, commodity networking, and commodity interconnects. Now, the elements that make up this end-to-end storage platform stack, starting from the storage, is storage spaces, managing the disks in my commodity JBODs, providing resiliency against media failure. We have Windows clustering, providing high availability against my node failure. We have Windows File Server, scale-out file server, providing scale-out data access for all that data underneath to my virtualized workloads as managed by Hyper-V. Now, this end-to-end stack is easy to manage because we have PowerShell and SCVMM integration, where I can manage my storage, my cluster, my file servers, my shares, my workload, all from PowerShell or SCVMM. Now, with SCVM specifically, I can throw out a pile of textbooks because it does it all for me with a few simple clicks. Now, this way to deploy storage is really no different than how it's deployed today with traditional storage, with the Fibre Channel or iSCSI storage array. Looking at the component level, they share very similar components. A storage array has Fibre Channel or SAS disk shelves. Storage spaces uses shared SAS JBODs, perform, well, essentially the same function. They both have some level of storage compute. My traditional storage array has, well, embedded CPUs and controllers and running proprietary software. Windows, we utilize a cluster of commodity servers running Windows. These servers are easy to manage, just like any other servers out there. And you can upgrade these servers as your data needs increase. The big difference between these two deployments is the protocol used to communicate between my storage and my virtualized workloads. With a storage array, I'm talking block. I have Fibre Channel or iSCSI. I unmask a LUN from my array, and I present it to my compute nodes. My compute nodes run in that LUN. With the Windows file server cluster, I'm talking file over SMB. I have a share. In fact, I have a share on a CSV, which aggregates all my storage in my cluster across all my servers, across all my JBODs from this CSV. I present this share to my workload, and my workload runs on that share. So file, block, Fibre Channel, SMB. But from the workload point of view, what is it really running? It has a bunch of files, and it's running on a LUN or running on a folder. That's just the exact same thing to that workload, regardless if it's a traditional storage array with block access or storage spaces with Windows file server cluster with file access. From the workload, access is the same, and the architecture is the same. From a capabilities point of view, my traditional storage and a Windows file server cluster also share very similar capabilities, perhaps with different names. Both have storage tiering. This is new in R2. Both have a form of data duplication. Both have availability. Both have a persistent write-back cache. And both do offloaded copies, just to name a few. Capabilities, architecture, both are very similar. No different than what you're deploying today. Before I talk into spaces, I want to walk through a case study. We have an internal engineering team called the Windows Release Team. Now, this team is responsible for managing what's called build symbols, which is just build data, essentially, across all the Windows teams, which each have their own source repository, and those source repositories have sub-repositories. It's a lot of data to manage, because we have so many Windows teams, and each team has a number of repositories. The problem with this team is that they had a number of issues. They had capacity issues, they had cost issues, they had resiliency issues. Even though they had 2 petabytes of raw capacity, 2 petabytes of capacity, that's a lot of storage in itself, but even though they had that much capacity, it was only enough to store 5 days worth of data. 5 days. There were so many Windows source repositories. Each day we're doing daily builds, generating a lot of data. 5 days. So you can imagine that that was not enough. And the problem is expanding that capacity was impractical because they had a mix of traditional storage and some servers with storage. So the cost and complexity of the architecture, and keep on expanding that, was not practical for the future. And because they had such a complex deployment, they couldn't ensure that their employment was on redundant power because they had so many servers. So they had individual points of failure. Also, because they were using servers, they were using a bunch of servers and distributing their data around, they had points of failures where they need humans to intervene and replace a server, pull out the data, and then put a new server back in and suck back in the data, which caused downtimes for certain teams as certain portions of the data were missing during that time. So they had a number of issues. But this team also had a number of needs. Windows engineering organization wanted about a month's worth of data retention, which seems pretty reasonable. But because their dollars per terabyte of their existing deployment was too high, they needed to dramatically reduce it. They also needed a scalable platform for the future as their data needs grew. They needed a platform that will support their data 5, 10, 15 years down the road. This is not possible with their existing architecture. So we worked very closely with them to deploy spaces And let's see what they got. Immediately, they saw a 2x, a doubling of their storage throughput with Spaces. Now, interestingly enough, when we were testing this deployment, we found that the storage Spaces was pumping out so much data, was giving so much throughput, that the network switches in the building were becoming the bottleneck. So we had to go to the infrastructure team and get them to overhaul the switches in the building to handle this throughput. And actually, we had to go get the adjacent buildings to overhaul their switches as well, because the way Microsoft networking works is that each building are interconnected. They tripled their raw capacity with the same budget. So they were given a budget. They negotiated a special budget for that year to replace a third of their existing deployment. Using that same budget, they replaced all of it. They went from $1,350 per terabyte with their traditional storage deployment to $450 per terabyte with storage Spaces. They cut their costs by a third. Through data deduplication and through this tripling of their capacity, they saw a 5x increase in the effective capacity of their storage. And because storage Spaces allows them to deploy their storage with so much more density, they saw a 6x reduction in the number of servers. They went from 120 servers to 20 with storage Spaces. They called 8 full racks, 8 full 42U racks full of gear. All the power, cooling necessary to support all that gear. So look down a data center aisle. 8 racks are now empty, or 8 racks are now missing. Or in some people's data centers, the whole row is just not there. So here's a little diagram of their deployment as it is today. They have 20 high-performance file servers, and they have 20 60-bay JBOD arrays with 3 terabyte disks. Now, this infrastructure is interconnected with a 10 gig network. But this infrastructure is connected through to the rest of the Microsoft campus through an aggregate 80 gigabit networking switch, or networking nexus. And through this 80 gigabit network, we have hundreds of build servers, Windows build servers, running builds every day for all the source repositories, for all the Windows teams, for all those sub-repositories, every day running builds. Pushing data onto these servers. We have thousands of engineers across Puget Sound, thousands of engineers and partners across Puget Sound, and Microsoft worldwide consuming that data for debugging, consuming that data for development. Every single week, we see 720 petabytes of data flowing through these switches every week. That is an incredible amount of data that Spaces is handling with their deployment, an incredible volume. So let's jump into what Spaces is. At the component level, Spaces uses very simple hardware. And here's a collection of some of the certified hardware that's available from some of our partners today. We have hardware from RAID Incorporated, from Data on Storage, and from Fujitsu. In fact, Data on Storage has a booth here on the floor. I would encourage you to please visit their booth. I have information on all the 3 partners. I would definitely encourage you to visit all partners' websites to find out more information. But we do have a partner here on the booth on the floor you can visit. But this hardware is very simple. I mean, you look at one of these boxes, well, of course, there's sheet metal, but there's a SAS backplane to connect your dual-port enterprise-grade SAS drives to. There's redundant power controllers to ensure I have resiliency against power faults. There's redundant SAS controllers to ensure I have resiliency against path failure. So even though this is commodity hardware, even though this hardware is cost-efficient, it's low in cost, it's ready for your data center. Resilient against power failures, resilient against link failures, and it has identification LEDs such that you can identify where your drives are and what drives have failed, such that you can easily replace them. Building up a Spaces deployment, just to outline some of the capabilities, let's start from 2 24-bay JBODs. So I have a total of 48 disks here. Now, I don't manage those individual physical disks. I don't manage 48 disks or however many disks I have in my deployment. I manage them. I aggregate those disks, and I create a storage pool. And this storage pool serves as the management point for these physical disks and can isolate these physical disks from another set of physical disks through creating different pools. From my storage pool, I carve out resilient virtual disks, or in other words, storage spaces with different characteristics. I can have different resiliency settings. I can have different capacities. I can have different performance characteristics. Spaces will natively stripe your data across multiple physical disks in the pool to maximize performance, to ensure that multiple disks service my reads and writes simultaneously. And with Spaces certified hardware, we get the concept of what's called enclosure awareness. When I create a resilient virtual disk, Spaces will attempt to place separate data copies on separate JBODs. So I place data copy 1 on JBOD left, data copy 2 on JBOD right. If JBOD right goes down, I still have the data copy on JBOD left. This is with Spaces certified hardware to identify which physical disks are in which JBODs such that it can put multiple data copies on separate JBODs. What if a disk fails? Because we spread out our data amongst different physical disks, we're also able to recover from a disk failure in a manner such that I can do it to simultaneous physical disks at once. So we have a test setup in our labs where we have 8 3-terabyte drives. I simulate the failure of one of those drives, and that drive contained 2.4 terabytes of data. We're able to rebuild that disk in 50 minutes. Rebuild that disk in 50 minutes, 2.4 terabytes of data. That's a throughput of 800 megabytes a second, far beyond the capabilities of what a single physical disk can do. And this is because we spread out our data amongst physical disks in the pool, and we can parallelize the rebuild process to be serviced from and to multiple physical disks. On REFS or NTFS volumes running Spaces, we have a service in the background that periodically scans for latent data corruptions, and it autocorrects wherever possible. We're easy to manage. We have extensive PowerShell commandlets that allow for scripting and remoting, and I'm going to show you some of those commandlets later today. We have integration into Server Manager. And most importantly, we have integration end-to-end SCVMM 2012 R2. I can manage my storage, cluster, workload, all in one. And through Windows File Server Cluster, we're continuously available. Now, I'm going to show, here's some of the examples of the resiliency settings we have. Mirror and parity spaces provide maintain 2 or 3 copies of my data. We recommend mirror spaces for all types of workloads. Mirror spaces will give you the best performance. Parity spaces, we recommend more for sequential workloads with large units of read and write, such as archive workloads. And a simple space is appropriate only for workloads that do not have resiliency or provide alternative resiliency mechanisms, such as replication. Now, you can take a look at this slide later on as the deck is available. Let's build up a clustered spaces deployment. I have in this case, two 60-bay JBODs. So that's an aggregate of 120 disks from these 2 JBODs. And I have 2 clustered file server nodes. I connect my JBODs to my file servers in a manner that each file server sees the same storage. So file server on the left has 2 cables to JBOD on the left and 2 cables to JBOD on the right. And this provides me resiliency against link failure. If one of those SAS controllers were to go down in either the file server or the JBOD array, I still can see my data. And the same thing with file server on the right. Both have 2 connections to each JBOD. And because SAS has so much throughput, my total of 8 cables there, 8 SAS cables, gives me 96 gigabits of raw throughput from my file servers to these 2 JBODs here. It's a lot of throughput for my storage. So on top of this, I take my 120 disks, I create a storage pool, like we mentioned before, to aggregate them. That's the unit of management. That's where I manage my storage. From my storage pool, I carve out multiple resilient storage spaces. In this case, I've created 3 mirrored spaces. But because I have multiple virtual disks, multiple servers, I need an easy way to manage my storage. Or at least I need an easy way for my workloads to talk with my storage. I don't want to go to each file server node, figure out what storage is on there. That's not going to scale as my deployment grows. CSV, cluster share volumes, on top of my virtual disks in the cluster, provide a unified namespace. I do whack whack cluster. I see all my storage in one flat view. One namespace, one point of access. And then with scale out file server, I share out this to my virtualized Hyper-V workload nodes. Now my workload nodes can move around because the storage is shared and because I have this one namespace. So even though my workload moves around between nodes, it still talks to the same place. It still talks to whack whack cluster, whatever folder you're talking to. This is what cluster share volumes provides you. Single namespace, manage all your storage, and presents all your storage. And this aggregation of compute and storage is, again, very similar to what many people are traditionally deploying today with a storage array. I can scale this out. I can add more servers. I can add more JBODs. But as I add more servers and JBODs and create more virtual disks, data access, still through CSV, still a flat namespace. All my storage is still in one spot. I can scale this out even more, going past the physical connector limits of my JBODs. I can add more server and JBOD units. My last unit, even though the units are not physically connected to each other, they can still talk to each other through the CSV. Network traffic, storage traffic, simply gets redirected through my high-speed cluster network. And as I add all these units here, I have all these virtual disks. Each unit has their own sets of virtual disks. My data access is still on this flat CSV namespace. The CSV namespace scales linearly as your deployment scales. And it's interesting. In this example here, we have each unit delivering approximately 1 petabyte of storage. We have 4 units here delivering 4 petabytes of storage. And Windows clustering allows you to scale up to 64 nodes. So given I only have 4 here, if I was to scale this up to 64 nodes, I'd have close to 64 petabytes of storage. It's Windows clustering and storage spaces. We have a couple of quotes from customers that are using Spaces today. Philip Moss from NTTX, which is a prominent hosting firm in the UK. He's able to use Spaces and Hyper-V over SMB to eliminate what he calls, quote unquote, a big lumpy capital expenditures. He can buy inexpensive storage and buy only what he needs and scale in a completely linear manner. So NTTX, he doesn't have 1 million customers coming at once. He has customers coming in as they seek to adopt NTTX's platform. He doesn't want to make a large investment up front. He wants to be able to add storage as those customers come in. Because where is he getting the money from? He's getting the money from those customers. Storage Spaces with Windows File Server Cluster lets him make this scale in a linear manner. Jeremy Russell from the Windows release team is able to use commodity hardware to achieve the same functionality of traditional storage at a far lower cost. Let's talk a little bit about our new capabilities in R2. We focused on further delivering minimized dollars per terabyte and capital expenditure for customers deploying storage. We focused on maximizing the IOPS per dollar you get out of your storage, further delivering on continuous availability, and minimizing your operational expenditures by making sure your storage your complete end-to-end solution is easy to manage. The first of which capability that minimizes the dollars per terabytes for customers' archival workloads is dual parity spaces. Rather than having to use triple mirroring, I can simply use dual parity, and I get resiliency against 2-disk failures for my archival workloads. And we've actually worked very closely with Microsoft Research in developing our dual parity implementation to ensure that rebuild times are faster than many industry implementations of dual parity. So the window of failure, of exposure to failure, is reduced with our dual parity implementation. Also new in R2 is support for parity and dual parity spaces in a cluster with CSV. So my parity spaces provide me not only resiliency against media failure, but high availability for my archival workloads. And uniquely with spaces, we provide integrated journaling. So what that means is that we journal, we log, basically, every update operation that we want to do to the metadata of our dual parity space, such that in the event of a power failure, spaces can recover from that event and bring itself back to a consistent state without the need of a dedicated battery backup. We journal, we have an integrated journal inside that's persistent on those physical disks. And it's not only against power failures, it's also against unplanned cluster failovers too. Any situation where I did not have a clean shutdown of my storage. Now let's talk a little bit about a different capability. We look at many common enterprise workloads. A lot of them, they have a very large data set. Well, of course, they have a very large data set. And a majority of that data is cold. Majority of that data is not very frequently accessed. It's just sitting there. We have a minority of that data that is frequently accessed. It's in active use. This is commonly referred to as the working set. So large amount of data, most of it's cold, and we have a working set that's much smaller. Come on. And that working set, of course, changes over time as your workload changes. So it's not a static working set in most workloads. We also look at what drives are available on the market today, or at least what's compelling in terms of customer deployments. We have 7,200 RPM hard disk drives, nearline drives. Current market, you can get a 4 terabyte 7,200 RPM drive for a very low price. This gives you the most compelling dollars per terabyte for your deployment. But the interesting thing is that these 7,200 RPM drives, even though they're optimized for capacity, they're not optimized for random IOs that you typically see in a virtualized data center. And interestingly enough, though, because they're high capacity, because they're low cost, it seems like a natural fit to store my cold data set. But because they're not very high performance, they don't naturally fit to store my working set. And on the other hand, I have solid-state drives. Very high performance, extreme performance. They're expensive, though, and they don't give me as much capacity. But by deploying solid-state drives, I improve my IOPS per dollar. But again, because I have a much smaller working set, it seems natural to deploy these smaller but more expensive SSDs to handle that. But it doesn't seem appropriate to deploy these SSDs to handle my cold data. So HDDs to handle my cold data and SSDs to handle my working set. Now I need an intelligent way to merge the two into a single namespace. And that's exactly what we've done in R2. With a single namespace, I can utilize the best characteristics of rotating media to store my large, cold data set at low cost. I utilize the best characteristics of SSDs to store my working set, my most frequently accessed data, providing the best performance for that working set, delivering me the best IOPS per dollar. And we do this in a single storage space. And interesting, we integrate very closely with the file system. The file system, in the background, measures the heat. Transparent to my workload. It measures the heat underneath my workload. Figures out what blocks are hot, what portions of files are hot, what portions of files are cold. My hot portions will be moved to the SSD tier, and my cold portions will be moved to the HDD tier. As my workload changes, we detect that change in heat, and we will move blocks out of the SSD tier as it gets cold and move blocks out of the HDD tier as it gets hot. This all happens in the background with minimal or any impact to your workload. And because we integrate with the file systems, we allow for administrators to assign specific files, to override the automatic placement based on heat for a file, and say that I want this file to be placed on the SSD tier. Or conversely, I want this file to be placed on the HDD tier. You can imagine the classic example to place a file in the SSD tier is a gold VM, or gold VHD, that provides the basis of thousands of virtual desktops. By placing this gold VHD on my SSD tier, I just increase boot time for these thousands of desktops. And I guarantee that boot time. Another capability that maximizes customers' IOPS per dollar is the write-back cache. And this is a persistent write-back cache. There's nothing stored in RAM. It's persistent to the disks. It's a per virtual disk write-back cache, utilizes available SSDs in the storage pool to absorb short-term bursts of random write activity to the virtual disks. It absorbs these bursts to not affect, to minimally affect, running workloads on that volume, and integrates seamlessly with tiering. So tiering, you can think of tiering as providing the best balance between capacity and performance, and the write-back cache absorbing short-term spikes in random write activity to your virtual disks. Now I want to show you a demo of the write-back cache and tiered storage. So I'm going to switch over to my other PC here, which has gone to sleep. So the question was, is tiering only SSDs, or can I use 15K drives? I'm going to answer your question. I'm going to work on my laptop at the same time. So if we compare 15K drives to 7.2K drives and SSDs, we'll see that 15K drives use 5 times more power than 7200 RPM drives, typically 5 times the power. And the current capacity of 15K drives is about 300 gigabytes, compared to capacity of 7.2K drives, which is 4 terabytes. If we start looking at that comparison between 15K and 7.2K, the jump between 7.2K and 15K, you only gain 2x at IOPS, but you lose orders of magnitude in capacity, and you lose orders of magnitude in power consumption. While the jump from 7.2K drives to SSDs, you don't really lose that capacity, because SSDs, well, you can get even up to 2 terabyte SSDs today. You can get, well, more commonly 800 gigabyte SSDs. You don't lose that capacity. You gain orders, absolute orders of magnitude in performance, and in power consumption is rather similar. So by making that comparison, 15K drives don't seem as compelling with tiering anymore. So with R2, we are using SSDs as a tier, and we're using HDDs as a tier. And we think it's most compelling for customers to deploy 7.2K HDDs, which provide the best capacity for their data. Does that answer your question? Yes. Let me check on this. My laptop just asleep. I'll take another question. Yes? So the question is, for the write-back cache, are you limited to the memory and system for the total size of the write-back cache? The write-back cache does not actually use system memory. It's a persistent write-back cache that utilizes the SSDs in the storage pool. So as I move my virtual disks around, it'll also move that write-back cache with it, and will not have that write-back cache in an inconsistent or missing state. Because if I use my memory and I have a cluster fail over, I can't fail over the contents of that write-back cache. So we ensure that it's persisted to the SSDs in the storage pool. And this enables mobility. Sorry, can you repeat the question?
How does that affect mean time between failures on the SSD?
The question is, how does the write-back cache affect the mean time to failure on SSDs? Is that right?
Yeah.
Okay. So I'm guessing you're implying that when I do more writes to the SSDs, it would wear them out quicker than they would before, right? So we're going to use the SSDs anyways. We're going to use them for tiering. As your data becomes hot, we're going to write to them. But having additional writes for my write-back cache, it really doesn't increase, at least substantially, the total writes to the SSDs. Because even if we didn't have the write-back cache and that data was active, we'd still move that data into the write-back cache anyways. So you'd still have that write anyways. And even if in the case of you just deploying SSDs, well, you'd actually have even more writes by deploying a pure SSD deployment versus having this tiering, where you have a portion of the writes going to SSD, a portion of the writes going to HDD. I hope does that answer your question? OK, it looks like I can connect again to my demo rig back in Redmond. But it's very slow. Switch over. So let's show you the write-back cache demo first. Remember I told you the write-back cache absorbs short-term, well, this is very slow, absorbs short-term bursts of random write activity to the virtual disks. I'm going to prove this to you. I have two perfmon windows. Perfmon window on the right is on a volume without a write-back cache. Perfmon window on the left is a volume with a write-back cache. The blue line is on both volumes is a workload that I'm running. It's the workload I really care about. And it's delivering me approximately 550 IOs per second on both volumes. Now, superimposed with this blue line, and I'm just not sure you can see it very clearly on this graph right now, is a dotted red line, which indicates the total IOs per second that this volume is servicing from all the workloads, from this blue line workload and from any other workload I'm going to introduce. I'm going to introduce that workload right now, and it's going to be some heavy random writes, short burst of heavy random writes. Let's see how the volumes handle them. On both perfmon windows, you see the dotted red line shot up. This indicates more work was done on both volumes, because I had my blue line workload and I had my large peak of random writes. However, the volume without a write-back cache, you'll notice when I did that write spike, my blue line workload I really cared about, saw a significant decrease in the IOPS it was able to deliver. Write-back cache, workload went on smoothly. Let's give another a spike in here. Again, write-back cache, smooth that random write workload out. Let's give it another one. Good measure. Write-back cache seems to be doing its job. Move on to the tiering demo. What I'm going to show you here is the seamless transition of a file that's currently completely located on the HDD tier of this storage space. I'm going to move this file to the SSD tier, but the kicker is I'm going to have an intensive I/O workload running to this file. So you can imagine you're running your SQL database against this file, or this file is your SQL database, or is your VM. How does tiering affect the workload? So you see a perfmon window here, and my workload is doing roughly 2,600 IOs per second to the file, give or take. Let's kick this file on over to the SSD tier and see what happens. So I've just did a PowerShell command to set the tier of this file to SSD, and I've immediately asked the file system to move it. Now the movement actually occurs in a scheduled manner. So if I waited for later on tonight, it would have moved it by itself. But I can also tell the file system to immediately perform the data movement. You can see that the IOPS of the file are already going up, because as more and more blocks underlie the file being moved to the SSD tier, my random workload starts hitting those blocks, and the IOs per second go up. So now the file is completely on the SSD tier. All the blocks that underlie the file are being serviced from SSDs. They were serviced from HDDs not too long ago. Now they're being serviced from SSDs. This transition between HDD and SSD was seamless. It did not affect the performance of my workload, did not affect, per se, your VMs, your SQL database. And it occurred quickly. Now, I want to give another demo that folks thought was very helpful. Looks like I lost that machine, too. Is there any questions while I get this machine connected? Oh, yes, sir. Sorry, can you repeat yourself? So the question is, with the write-back cache, how do I maintain cache consistency? So we persist the data to whatever available SSDs there are in the pool. We simply use that capacity from those SSDs to serve as a staging area for my writes. And we have what's called a dirty region tracking to ensure that any updates to those regions are tracked in a log, a journal, and that we can, for instance, if there's a power failure or an unexpected node transfer, that we can look at this and figure out what is the state before and bring that write-back cache back into a consistent state. And it does this without the need for a battery because this is all journaled operations. Does that answer your question? Yes, sir. So the question is, if I'm running an automatic tiering mode, which is by default, what is the schedule? What is the frequency of data movement? What is the settings I can change? So tiering is a scheduled task in the system. We put this task in a system on by default when there's any tiered volumes that are mounted. This task runs, we currently set it at 1 a.m. every day. You can configure it. You can configure it to run during maintenance time. You can configure it to run twice a week. You can configure it to run twice a day. This is configurable based on your workloads, based on your business needs. If you see you have downtime, or if you see you have downtime perhaps once a week, then you can run it that time. If you see you have downtime 3 a.m., you can run it that time. It's all configurable because we use the scheduled task UI to make those. You can make those changes through the scheduled task UI. Absolutely. And you can also adjust the percentage of the SSD tier that we can replace at any processing time. So for instance, if I have 100 gigabytes of SSD tier, I can tell Windows to replace up to 50 gigabytes of that SSD. For instance, if it's detected that 50 gigabytes of the data is cold, it will move that data out. You can limit the amount of the SSD tier to egress at any time to reduce the thrashing back and forth if you have a workload that is changing very frequently. Does that answer your question? Let's just run through this here. So I had a session yesterday, and a lot of folks found this PowerShell walkthrough very helpful. So I want to do this again. I apologize if you've already seen this, but perhaps you can pick up on something that maybe I missed. So the first thing when I create a storage pool is I need to get physical disks in my system. I need to find out what disks I want to use for my storage pool. So in this system here, I have 8 disks, but only 6 of them are available for use by tiering and by storage spaces. And you can determine what disks are available through the can pool field. So you see 2 of them are false and 6 of them are true. And of the 6 that are true, I have 2 that are 200 gigabytes, and I have 4 that are 1 terabyte. So I'm going to go ahead and grab those disks that I can use with the can pool field as true through PowerShell filtering and throw that into the $disks variable. Now, from this $disks variable, I have that collection of physical disks. So I'm going to create a storage pool. I pass in storage spaces as the storage subsystem, and I pass in my friendly name that I want. I'm going to call this tiered pool, and I'm going to use those disks that I just selected. So right now, Spaces is writing its metadata out to all those physical disks. And Spaces does this in a unique manner, such that each disk in my storage pool has unique awareness of each other disk in the pool. So for instance, if I was to pull one of these disks from the system, only one of these disks, put it over in another system that's completely separated from this system, this disk would pop up and realize that, hey, where's all my buddies? Because he knows that he's missing those other 5 disks in the pool. He is uniquely aware of all the other disks in the pool. So now I have my storage pool. It's created and it's healthy. Let's take a look at the physical disks in the pool and look at what type of media they are. We've added this media type field in R2 to support tiering. Windows will automatically detect Spaces certified hardware, Windows certified hardware that properly reports themselves as SSDs and properly reports themselves as HDDs. In this case, I have 2 SSDs and 2 HDDs. If you're not using Windows certified hardware, or Windows has not detected the media type, it would show up likely as undefined. And we have PowerShell commandlets such that you can override the media type of physical disks. I can set this undefined disk to SSD or HDD, as long as there's no data on that disk. Yes, there was a question. So the media type is there before the storage pool is created, but you can only set it after you add it to a storage pool, because we persist that as part of the pool data. Yes. Yes, sir. So the question is the write-back cache limited to only tiered spaces? And the other question was, is the size of the write-back cache limited by the SSD tier you specified? Is that correct? So to answer the first question, and I apologize for not making this clear earlier, is that the write-back cache can be used on non-tiered volumes as well. It can be used on tiered and non-tiered volumes. And to answer the second question is that, and I'm going to show you this in just a second. So I created my storage pool. I just checked my physical disks. They have all the right media types set. They have SSD, they have HDD set properly. So now I'm going to create storage tiers on my pool. I'm going to create an SSD tier, and I'm going to create an HDD tier. Spaces will automatically identify whatever physical disks need to go in those tiers. Now that I have the tiers, and I've actually put those tiers into variables so I can easily create my virtual disk, but now that I have those tiers, I'm going to create a tiered virtual disk. I pass in the name of the storage pool. I give that virtual disk a friendly name. And I pass in the storage tiers to use for allocation. I pass in the SSD tier, and I pass in the HDD tier. And I also pass in the size I want through the storage tier sizes variable there. I pass in 150 gigabytes for my SSD tier and 1.75 terabytes for my HDD tier. I want this space to be created as a mirror. And by default, Spaces will create a two-way mirror that keeps 2 copies of your data, as you saw earlier. And at the end here, I pass in the write cache size, which is the size of the write-back cache that I want to use. Now, when Spaces goes and create this tiered virtual disk, it will take that 5 gigabytes, it'll take that 150 gigabytes, and it'll go find 155 gigabytes of capacity from the SSDs in my storage pool to create this virtual disk. So I'm going to create this virtual disk. And it's created, it's healthy, and it's about 2 terabytes. The size of the virtual disk is determined by the adding of those 2 values in the storage tier sizes. The write-back cache is not counted as part of the size of the virtual disk because it is a staging area for my writes. So it's not part of that virtual disk. It's simply a staging area. It does not get presented to the file system. So I'm going to initialize this virtual disk. I'm going to format it with NTFS and give it a drive letter. And then I'm going to copy some test files to it. I have 2 test files on that volume now. I have archive1.vhdx and marketingpoolvmparent.vhdx. So I'm going to pin my pool parent vhdx to the SSD tier, and this is command for it. Set file storage tier. I pass it a file path. I pass in my desired storage tier, which is the SSD tier on that tiered virtual disk I just created. So I'm going to pin this. Oh, error. Let's see if this one works. Oh, I apologize if something seemed to happen here. Just worked 5 minutes ago. So what you would have saw Let's see if this one works. Well, something seems to have happened. So what you would have saw is that this pinning operation would have, of course, succeeded. And you would have saw that the SSD tier, the file that I pinned to the SSD tier, Windows would have showed you that it was completely on that tier. The file that was pinned to the HDD tier, Windows would have showed you that the file was not on that tier, and that I could then immediately trigger the data movement to get that file onto the tier. Now, again, this would happen normally in the background as a scheduled task that would be triggered at 1 a.m. daily. You can configure that. But in this case, I wanted to immediately move it. And once that was immediately moved, you would have saw that the status presented to you through PowerShell was that it was updated and that was now completely on the tier. Demo gods don't like me today. But I move on. So you saw this picture before of the Windows file server cluster scaled out. Our new R2 capabilities, dual parity, tiered storage, write-back cache, integrate right into that. In this case, I have tiered mirrored spaces. I have a dual parity space for my archival workloads. And now my JBODs have a mix of SSDs and HDDs. With commodity storage, Windows gives you the flexibility to deploy storage of different configurations. I can go for the capacity optimized approach, giving me the highest capacity, the best dollars per terabyte. And we have many customers doing that today, such as the case study you saw earlier with Windows Release Team. We have the performance optimized approach. We have many workloads out there that require extreme IOPS. You can do this with Spaces. We have a partner on the floor. They have some hardware that they can show you that has 24 disks in a 2U JBOD, and that in a 3-node cluster can give you 1.45 million IOPS. If I took 2 of those JBODs together for 48 SSDs, we've seen in our labs 2.7 million IOPS from that cluster. 3-node cluster, 2 JBODs full of SSDs, 10U worth of gear, 2.7 million IOPS. Spaces can scale to that. And we have a balanced approach. Customers that have workloads that have a portion of it which need high capacity, which need high performance, and a much larger portion of it which need high capacity. We give you this with tiered storage, giving you the best balance between performance and capacity. And this is possible, this is feasible, because we use commodity components. Commodity storage, commodity disks, commodity servers, commodity networking, commodity interconnects. Here are the vendors that currently produce Spaces certified hardware. We have RAID Incorporated, Fujitsu, and Data On Storage. Now here are the web addresses, and you can when you download this deck, you can take a look at their solutions. All these 3 partners provide high-performance servers, high-performance storage. They provide a number of flexible solutions to meet your varying data center needs, either in different types of form factors or different densities. So we would definitely encourage you to contact these vendors. And of course, we are working with many other vendors to get Spaces certified hardware available in the market. So you can watch for that as time goes by. But of course, we would encourage you to contact your vendors to determine what is their support for Spaces. Do they provide Spaces certified hardware? We definitely encourage that. Windows Server 2012 is a key component to your cloud. Provides cost efficiency, maximizes your IOPS per dollar, minimizes your dollars per terabyte. Provides scale, provides capacity, provides continuous availability through the Windows file server cluster. And you've seen customers, you've seen the release team, you've seen what they got with Spaces. They tripled their capacity, they doubled their storage throughput. Their network became the bottleneck because Spaces pushed so much throughput. And with dedupe, they increased their capacity 5-fold. And they significantly increased their data density to cull 8 full racks full of gear. This is with Spaces. This is with the Windows file server cluster. There's a number of other sessions, but of course we're at the last day. But when you look back, you'll see a number of other sessions, and you can look at them online. and they all have great content, so I'd highly encourage you to look at that. And in addition to the questions that I'll help answer here, you can find us at the storage booth for the rest of the day for any other questions you may have. Thank you very much. All right, I'll take questions. So the question is, how does Spaces deal with different sizes of disks? Because Spaces spreads its data around, it can simply spread the data across those different size disks and use only portions of the disk, for instance, for portions. I can actually draw you a diagram for that. It'll better explain how we work. But yes, it'll optimally use those different size disks as best as it can. Yep.
I thought I remember hearing earlier today that 80% of the RAM could be allocated for write-back cache. Did I mishear that?
The question is that you heard earlier today, 80% of the write-back cache of the RAM is allocated for write-back cache.
Or you could allocate up to. I thought
Okay. I
I
think you're talking about the CSV block cache. That's at the CSV layer, and that's a per node cache. Yes.
CSV, what was that?
CSV block cache. So CSV has its own cache that utilizes the memory on your servers to provide a block cache for your data. That is different from the write-back cache. Write-back cache is persisted to SSDs. A CSV block cache is just an in-memory. It's mostly as a read cache.
As a read cache?
Yes. Dedupe has its own cache as well. So if you're deploying Dedupe, because you don't get the CSV block cache with tiering, that is a limitation in R2 because of the way that we had to do redirection such that such that we can see heat from multiple nodes. We couldn't interop with the CSV block cache. But saving grace is that the Dedupe also has a cache that, and I believe you saw a demo in Jose's and Alden's session where the Dedupe cache significantly improved boot times of the VMs. Yes, sir. Yes. So Spaces doesn't use the offloaded data transfer command set. It instead, because we have that separation, I'll pull up a diagram. Because we have that separation of storage and compute, let me just pull up this diagram here. Probably best explain it. So with the traditional storage array, offloaded data transfers basically reduces or eliminates the process of moving the bits between my compute nodes and the storage and back again to perform the copy. With a storage Spaces cluster, we actually do the same thing. So when a Hyper-V node or a management node performs a copy between the SMB shares served out from my storage compute, which is my clustered file server nodes, we will actually offload the process of copying the data to between those clustered file server nodes. So I don't have the traffic that goes up from my storage to my compute nodes all the way back down again. And that accomplishes the same goals of offloaded data transfers, to reduce or eliminate that network traffic on the virtualized workload layer. But does that answer your question? But we don't use the ODX mechanism. We use a different mechanism that's available through SMB. Yeah. Thank you. Yes, sir? Yes. The question is, or the comment is, the comment is that we're no longer doing RAID. We're giving the intelligence to Spaces to manage the data, and that's absolutely correct. Spaces, I stick inexpensive HBAs, host bus adapters, into my clustered file server nodes instead of RAID cards or instead of purchasing a traditional storage array. Windows provides the intelligence to utilize those simple HBAs, utilize those commodity disks, and make your data resilient, providing high availability, providing high performance. Windows does all this logic now. Yes. So you're not paying for that logic anymore. Yes, sir. So the question is, if he wants to go test Spaces, does he need to go buy a JBOD, a certified JBOD, or can he use local disks? And absolutely, in your test labs, in fact, in the demos that I was using, I was just using VHDs in a VM. We don't recommend that for deployments, but you can absolutely do that for their test labs. You won't get certain features such as enclosure awareness, LED blinking, drive identification, but it will work in some scenarios. But I certainly wouldn't count on it for maximum performance management and so on and so forth. Yeah. Yeah.
Hello?
Oh, yes, sir.
So our environment is 100% virtualized in VMware. So server 2012 will be virtualized. And we are running off of NetApp SAN. How would we encompass some of these benefits of the clustering that 2012 has in that environment? Because we're not going to do JBOD, obviously. We already have a whole bunch of this.
Right.
And we're not necessarily doing, iSCSI with fiber channel. We're doing FCOE at a 10 gigabit throughput. So if I assign a hard drive to this VM, whether it's solid state disk or 15K disk or 7200 RPM disk, how can I take advantage of some of the stuff that the server does?
So the question is, with a traditional storage deployment, in this gentleman's case, FCOE, how does he take advantage of tiering and some of these capabilities that I just showed you? So because you're using a traditional storage array, adding spaces on top of that, whether or not directly on your file server nodes or within your VMs, is not recommended, and we don't support that configuration. There are a number of management issues that we run into because perhaps errors are not bubbled up from the array up to the virtual disk, so your users would not be aware that an error has occurred, and administrative action needs to be taken to repair that. You might also get some instances of inconsistent performance because you've added extra layers of indirection. It just complicates the deployment so much that we wouldn't recommend it for spaces, and it's not supported by Microsoft. Yes. And even exposing VHD files to within your VM, that also adds another layer of indirection. We really recommend this deployment of commodity storage, shared SAS JBODs. I have commodity file servers, put spaces there, and I share that out to my compute nodes. And that really gives you the best cost for your deployment. Yeah. But we cannot put spaces on top of the existing storage, traditional storage.
Now, this is only if you want to do high-level computing and you want to let Windows sort of act like a SAN for you.
Yes.
Right?
Yes. This is Windows is providing your end-to-end storage or your virtualized workloads.
Now, did they do away with DFS, or DFS still exists in 2012?
Sorry, can you repeat that?
Did you do away with DFS, or it still exists?
The question is, did we do away with DFS? And DFS is absolutely there. And there are scenarios for replication that people would still use with DFS. This is really providing resiliency against media failure, providing easy management. We're managing all those physical disks down to aggregate that into a pool, creating a resilient space, putting your data there. DFS is really replication between volumes.
Thank you.
Yeah, thank you. And of course, you can replicate your virtualized workloads with Hyper-V replica.
Yeah.
And we recommend that, for instance, between data centers. Yes, sir.
If you don't have the need for SSDs, you have all HDDs, what is your write-back cache leverage in that case? Does it just leverage other HDDs in the non-tiered scenario?
So the question is, if you don't have any SSDs, you only have HDDs, what does the write-back cache do? Is that the question? So if you don't have any SSDs, you cannot create a write-back cache because there's no media to take that from. If I'm using HDDs as the write-back cache, it's not really compelling. I haven't really done anything to speed up my workloads. So we really recommend a small number of SSDs if you're not using tiering, just to serve as your write-back cache. And you can get small SSDs on the market today for that purpose. Does that answer your question?
Yeah, absolutely.
Yeah, and you can, if you have multiple, if you have like say a 200 gigabyte SSD or a couple of those, you can use that space for multiple virtual disks and have multiple write-back caches, or multiple virtual disks, each with a write-back cache, and it'll split up the SSDs.
Would
Yes.
you ever not tier and just use SSDs for write-back cache? You'd have a single tier, but you do write-back caching on SSDs?
Yes, absolutely. I can create. The question is, can I not tier and just use the write-back cache?
Would you want to do that? Is there any scenario that makes sense?
I'm not sure if there's any scenarios that make sense. If I have a really high capacity, very high capacity volume, Some of the data is eventually going to be hot. And it's very compelling just to at least put a little bit of tiering in there to make that access of that data to be quick. So we'd always recommend, for most workloads, and I'm not sure if maybe there's a specific workload out there that has no hot data, that you just want to write back cache to ensure that certain random, if you get occasional random writes, those are staged quickly. Well, I can't name any specific workloads where you would want to do that. Yes, sir.
Those PowerShell commands you were running right on the SAS box, correct?
Yeah. Well, I was actually doing it from within a VM because I don't have enough hardware to do a separate demo for that. But absolutely, they would run.
Provisioning on the SAS box.
You would do the provision. Well, you do it on your file server connected to that shared SAS JBOD. The shared SAS JBOD is a very simple piece of hardware. It's just disconnecting to a backplane, connecting to a SAS controller, and your server provides the intelligence, not the SAS box. Yeah, all the SAS box does is has identification for the drives. It does the LED blinking. It doesn't have a lot of intelligence in it, and that's why it's cost efficient.
Is there a graphical interface to Spaces? Also?
Absolutely. We have Server Manager. You can create spaces, create pools, configure tiering. You can use SCVMM to do it all. A gentleman at the back had a question?
Yeah, so the diagram that you showed originally had the server with a shared SAS HBA connecting through to the shared SAS JBOD arrays, right? But at the low end, you only had 2, but then you mentioned that you can scale out to 64.
Yes.
When you're getting to that level, you're no longer doing point-to-point connections, so you're doing some sort of shared SAS switch of some kind?
Yes, so let me pull up that diagram. This one, right?
Yeah, so once you start scaling that out, you're no longer doing point-to-point, right?
So the question is, once I've expanded from the previous diagram to this one, how is the connections being made? So we look, so based on whatever hardware is available on the market today, these 60-bay JBODs have 2 SAS modules, each with 4 ports. So these JBODs connect to a maximum of 4 servers. So that's why I've separated like this. I have 4 servers, I have 4 JBODs. And this works. This is all shared SAS. So this is all interconnected. This unit here is not connected to this unit in terms of SAS. But the connection happens because they're all in the same cluster. And the IOs, if I hop up there, gets redirected through the CSV. So this node can access data on this through CSV. It's all in the same namespace. If I do a read or a write, it simply gets redirected through this cluster network down to over here. As you add more of these units, my CSV remains linear, remains flat. So I don't have, and yeah, does that answer your question?
Yes, thank you.
Yes. Sorry? In this case, it would be, 2 each, so 8 cables per server, absolutely. And with SAS HBAs today, typically has a maximum of 4 ports, so I would just need 2 SAS HBAs. And they're relatively inexpensive, these HBAs. Yes. Oh, yes. I'd have to double check with the clustering team on that. Yeah, we'll double check. Windows clustering supports up to 64. Yes. I'll have to double check what the limitations are and what the ramifications of those limitations are. Yes, yes, sir.
When you configured the tiering, you chose 150 gigs for SSD. Does that optimization report help you identify the size of your working set of data? And if that changes over time, how would you become privy to that?
Yeah, so the optimization report tells you the efficiency of the utilization of the SSD tier. And if you were to add more SSDs, what benefit would you have? We actually have like a graph, not really a graph, it's just like a text output showing 0 to 100% where you currently are at, what your SSD size is, and if I were to add more SSDs, how much more percent of my quote-unquote working set would be contained within the SSD tier. So you can use that to make the trade-off between cost of those SSDs and the contents and how much the SSDs would contain your working set.
Does that become an operational task then in your release environment where maybe your working set changes over time and you don't want to just leave it stagnant at whatever the current setting is?
Right.
You make that an operational task usually then?
What do you specifically mean by operational task?
Like, if it's changes over time, do you have someone monitoring it outside of that scheduled task to increase tiering, let's say?
So we would expect that an administrator would initially set a SSD tier size, and then if he's seeing some perhaps workload inefficiencies, or perhaps he wants to figure out, oh, how efficient am I using my SSD tier? Did I really put enough in there? He would look at the report, but we don't expect administrators to constantly go back and look at the report to see how well they're doing. We expect once they've created it and perhaps adjusted it maybe once, even if then they would have a system they can just let it run and would handle their workloads. Yeah. Yes. So the question is, are there any limitations in storage protocols? Spaces supports USB, SATA, and SAS drives. Before clustering setup, our requirement is that you have SAS drives that support persistent reservations. And we have with the Windows clustering team, they have a cluster validation wizard that can determine if your drives and your entire configuration, as it's configured and plugged in and set up, is compatible with clustering. Yeah. So you can use that wizard to determine if your configuration, if your drives really supports clearing or not. And we've seen cases where certain drives, even SAS drives, don't support the right command sets for tiering. Not for tiering, but clustering. But that's significantly improving right now with our logo programs and so on and so forth. Yes? So the question is, because we have automatic tiering between SSDs and HDDs, is new data coming in first staged in the SSDs? That's the question, right? So with the write-back cache, we expect that most new data to be staged in the SSD tier. And the write-back cache helps those small random writes that occur. Now, because HDDs are not optimized to service those small random writes, we put the write-back cache in to provide a staging area. But larger sequential writes can be serviced from the HDD tier because those rotating media drives can service these sequential writes much quicker with higher throughput than they can those random writes. So large sequential writes, we put the HDDs, and small random writes, we put on the SSDs. Yes. If we don't have write-back cache enabled, is it the same thing? So without a write-back cache, there is no staging mechanism for new writes. New I/O would occur wherever the file system puts allocation as. Yeah. So the write-back cache is a good way to provide that staging. So we'd always recommend configuring tiered spaces with an appropriately sized write-back cache. Okay. Yeah. Sure. So cluster in boxes are certainly interesting solutions. Of course, we would want them to be Spaces certified if they produce a cluster in a box like that. I don't have any more details on that, unfortunately. But we would encourage you to ask them if they have more details on that. Yes, sir. There's a gentleman in the back.
Write-back cache, your phrase is, we use small random writes. What is small?
So we have a threshold in our spaceport driver that determines what quote-unquote small is. We're continuing and tuning that threshold as we speak. So I can't give you a definitive number as we haven't settled on the final number just yet.
Is small at least a megabyte? Because that's where VHDX.
Oh, it would be much smaller than that. Yeah, absolutely much smaller than that. Probably closer to 128K-ish.
The actual share that's in the unified layer, is that actually backed by more than one, I'd call it pod of scale-out cluster? So does that actually get replicated when you add a new expansion out across multiple pods, if you will?
So the question is, as I add more of these quote-unquote pods, does the data get replicated across the pods? Is that the question?
Yes.
The answer is no. The data doesn't get replicated. I can configure the data to be replicated. If I have all virtualized workloads, I can, of course, have Hyper-V Replica say, I want to replicate all the all the VMs that are running that have storage on here, and I want to replicate it here, that's absolutely possible. But the point of adding more of these quote-unquote pods is to add more capacity. Add more capacity, add more data capabilities.
So is it possible to do that without outage?
The adding more?
The replication.
Oh, yeah, absolutely. Hyper-replica that works without outage. It just works transparently. Yeah. I can add more storage without outage. I can replicate storage without outage, absolutely. I can move around my workloads that are running on top of this CSV without outage. All that is supported by Windows today. Any?
If you needed to decommission one of those because of maintenance, or just because it's a hardware refresh, you could get all the data all.
So in the case of decommissioning or, for instance, upgrading or servicing these, you would service them one at a time. I service this one. I service this one. I make sure I move the storage off and have the storage then owned by another node. And I service this one and bring it back online. Then I service this one, then I service this one, then I service that one. And that continues to give me continuous availability because there's always a path to the data. So I just service them one at a time. It still prevents you from getting an outage. Yeah.
So you mentioned earlier that it could sustain a power failure. So does that mean the commit back is once it's written to disk? Right. So
Yes. Yeah, it's journal, so we commit it before we move on.
So how would you think that would compare to some of the larger storage arrays where you've got the flash cache or various caching mechanisms?
So the question is, how does a journal solution compare to storage arrays?
And heavily loaded thousands of clients kind of scenarios?
I don't have direct comparisons, but I can speak to what our capabilities can do and what our capabilities can do for the dollars per terabyte that you get for the storage. And I discussed that today. Yeah. I don't have a direct comparison between what the storage arrays can do in terms of their journaling, if they have journaling.
I'm talking more about the committing, so committing it really at a flash layer versus
I don't have that comparison. Yeah, I don't have the. Unfortunately, I can't crack open their source code. I don't really know what they're doing in terms of committing and data persistence. They have a lot of software in their stack, and I'm not really sure what they do in terms of that. All right. I don't know. Yeah, sorry, I don't know. I don't have that comparison. Yeah.
Do you understand my question?
Yes, I understand your question. Yeah.
Where would I find
Well, we would encourage you to try it.
Right.
I mean, that's getting your hands dirty. That would be the easiest way. Yeah, that would probably be the easiest way to get unbiased data. Because I'm sure if you ask a traditional storage array vendor, they perhaps would give you biased data. So definitely try it out and see what you get. Sure. Absolutely. Right. So actually, Spaces does support what's called NVMe cards. Spaces does support it, but it only supports in a non-clustered configuration because the NVMe card is only on that one node, right? So we do support that in non-clustered configuration, and you can use that for your write-back cache. But if you have replication, then that could be as a means of providing persistence across different nodes. But yeah, the current state of the NVMe market is that there really is no shared NVMe at this point. It would have to be through some SAS or some other protocol, and that's yet to be developed. Yeah. But there is certainly compelling reasons to do so. I mean, SSDs have great capabilities, absolute great capabilities, and a great price. Flash cards have a different set of, flash cards service a different set of users than SSDs. I'm not sure. Yeah. So we differentiate based on what the disk reports as its type. If it's an SSD, it's an SSD. Yeah. But I mean, our architecture allows for more tiers in the future, easy addition of more tiers. So as in the future, you can possibly envision a whole slew of different types of tier attributes. But we've limited in this release to SSD and HDD. to store that common enterprise workload. Large data sets, cold, small working set. Yeah, and that seems to be the most compelling thing for this release. Yeah, I hope that helped.
If you have non-certified storage, and you get some of the capability by tagging, say, one shelf and another shelf
So the question is, if I have non-certified storage, can I tag shelves manually? I actually had the same question yesterday, and I'm going to look into that. So if you give me your card, I can find out for you, and I can give you that information. But even if you could do that, you still wouldn't get identification such as LEDs to specifically identify the specific drive inside that enclosure. And I mean, enclosures are large, so wouldn't want to pull the wrong drive. So we would always recommend Spaces certified hardware. Oh yeah. Right. Yes, sure. I will look into that. Just hand me your card, and I'll find out for you. Taking the enclosure ID for a set of physical disks. Yeah, that's what he wants to do. And probably slot number as well, right? Yeah. So the question is, when data is desaged from SSDs to HDDs, does it move the blocks or does it move the files? So the write-back cache occurs at the block level. It occurs in spaces. So we would move the blocks. And that blocks would really be the underpinning of that file as managed by the file system. But it's transparent to the file system, so the movement occurs nonetheless. Yeah. Does that answer your question? Because spaces manages where the data is, and the file system lies on top of spaces, so it's completely abstracted from all that. Yeah. Sure. Oh, yeah, we move sub-portions of files. And the interesting thing is, oh, yeah, absolutely. If you look at a simple VHD file, and let's just like a VHD file that you boot, not all of it is hot. Only a portion of it is hot, and a lot of it's cold. So it would be silly for us to move the entire file. So we just wasted a lot of space. So we track heat in 1 megabyte chunks, and we looked at this to find the best balance between how much data we track for the entire volume, for all the blocks of all the subfile portions of your volume, versus having the right set of granularity. And we found that 1 megabyte was the optimal size. So we track heat in 1 megabyte, and we move the between tiers at the file system level. The write-back cache occurs at the block level because it's integrated in your space. Yeah. So we move data at 1 megabyte, we track data 1 megabyte, and the write-back cache is at the spaces level, the spaces concept. Does that answer your question? Oh, great. Yes. So the gentleman is asking, is there a place for white papers for R2 capabilities or even for 2012 capabilities? We have a number of white papers out there. Again, if you give me your contact information, I will go point you to them. We are, of course, continually working on more documentation. Just in the past year, we've just been heads down focusing on R2. And this one-year release has really been busy. But yeah, we are producing collateral to help customers. Yeah, oh yeah, for sure. Just give me your card or fire me an email, brian.matthew@microsoft.com, easiest thing in the world. Yeah, all right. And yes?